Welcome to the video for C2.3.3 where we're going to look at bulk properties of materials. So just as a start, I want you to pause the video and see if you can work out what the bonding in each of these materials is. Okay, so hopefully we've looked at methane here, which is CH4, and we realised that both carbon and hydrogen, so both of these are nonmetals, so that's covalent. And it's not one of the giant covalents, it's simple covalent. And then hopefully we can look in the periodic table and see that sodium's on the left, so it's a metal, and chlorine's on the right, so it's a non-metal. So because you've got a metal and a non-metal together, that makes that an ionic substance. Mg is just one metal by itself, so that's metallic. Carbon is a non-metal, so it's covalent. And when we've looked at all the different allotropes of carbon, they've all been giant covalent. So magnesium is a metal, iodine is on the right hand side, so it's a non-metal. So when you've got a metal and a non-metal, that's going to be ionic. And then all of these, so carbon, hydrogen, and oxygen are all non-metals, so that's got to be covalent. And that's not one of the examples we've learned, so it's going to be simple. Iodine is just a non-metal, so that's also going to be covalent. And again, that's simple. And steel, we haven't looked at alloys yet, but steel we know is a metal, so that's just going to be metallic bonding. Okay, so there's just the answers in a bit more civilized form. Right, so our learning objectives today. So we're not really looking at anything new in this lesson. What we're doing is we're tying together lots of different things that we've done in previous lessons. So we're going to look at the bulk properties of materials and how that relates to the nature and the arrangement of their bonds. So we've already met the different types of bonding. So we've met ionic. So ionic is between a metal, which loses electrons, and a non-metal, which gains electrons. Covalent, whether it's simple or giant, is between non-metals, where they both share electrons, and metallic is just metals. So we've got to think about where we find these. So ionic, as I've already said, is between a metal and a non-metal. Metallic is just metallic elements or alloys, and covalent is between two non-metals. And that's either simple, where you've got small molecules with low melting points, such as water, or you've got giant macromolecules, where you've got really large molecules with high melting points, so diamond graphite, silicon dioxide, for example. So most covalent compounds are going to be simple molecular. So when we think about melting points for these, so this shows, so these are our water molecules. And then these dotted lines show the intermolecular forces. Now, if you don't like that word because it's a bit long and fancy, you can just describe it as the forces between the molecules. So here and here, you've got the covalent bonds between the oxygens and the waters. So remember, we can draw them out like that with the lines representing covalent bonds. So these covalent bonds are very strong. But when we melt a substance, we're not breaking those covalent bonds. The water molecule stays intact. So when we're melting a substance, what we're doing is we're breaking the intermolecular forces. So we're overcoming the weak intermolecular forces. And because they're not very strong, it doesn't require much energy. So the melting point is going to be quite low. So most simple molecular compounds are, or even some elements are, simple molecules, such as the group 7s, hydrogen, nitrogen, oxygen. So any of these substances, they're normally gases or liquids because the melting points are quite low. So covalent exceptions are when we've got giant covalent structures. So most of the examples you've looked at for these are the allotropes of carbon, but you might have also looked at silicon dioxide. So when these melt, because they're one, we've got to remember that these are basically one big molecule. So there's no forces between the molecules because there's only one molecule. So there aren't any weak forces between the molecules to overcome. So whenever these melt, I've got to break every single one of these covalent bonds, and covalent bonds are very strong. So because there's lots of them and they're strong, it's going to take a lot of energy. So the melting point of giant covalent structures are always high, usually very high. So ionic bonding. So ionic bonding is between a metal and a non-metal. So the metal here is positive and the non-metal is negative. And you've got this repeating pattern of positive and negative ions, which are very close together. And because you've got a strong attraction between the positive and negative ions, then you've got a strong force of attraction that needs to be overcome. And therefore, you're going to get high melting points. So the last one, we're going to look at metallic bonding. So here, so this diagram is not labeled. So these are our positive metal ions. And these are our delocalized electrons. Okay, and you've got a strong force of attraction between the positive metal ions and the delocalized electrons. And because that's a strong attraction, you're going to need lots of energy to overcome that, so the melting point is high. So using the ideas that we talked about on the previous slides, I want you to pause the video, copying this table into your notes, and complete it using what we've just discussed. Okay, so hopefully this is what we found. So you can fill this in with some examples. So a simple molecule, we could use an example like water. Giant covalent, you could use the examples of diamond. Ionic lattice, the most common example is NaCl, and metallic, you can pick any metallic element. So I'll just pick Mg. Okay, so simple molecule, low melting point, the rest are high, and these are the reasons. I'm not going to go over them because we've gone over them on the previous slide. So now we're going to look at whether they conduct electricity or not. So now we're looking at whether there's any mobile charged particles. So most covalent molecules, so all simple, so most covalent molecules, including all simple molecules, there were no delocalized electrons and there are no ions, so they're all insulators. The only exception to this is some of the giant covalent structures. So the covalent exceptions are, we've got some allotropes of carbon. So graphite, graphene, and nanotubes have all got delocalized electrons because each carbon's only got, so if I look, each carbon's only got 3 covalent bonds. So if I look at this one here, I've got 1, 2, 3 covalent bonds. So it's got a spare electron which becomes delocalized. Now, remember when we look at this one only appears to have 2, but really that structure continues past the bit of the diagram they've drawn. So what you see is, because we've got these layers of carbon hexagons, the electrons can then, which are delocalized, can whiz up and down between the layers, and that's what conducts the electricity. So ionic bonding is a bit more complicated. So the charged particles we've got here are ions. So our ions are our charged particles. But in a solid, such as the diagram that so this particle diagram shows a solid. So in a solid, those particles just vibrate. So they can't move past each other. So therefore, because the charged particles can't move, they're insulators. But when they're either melted or dissolved, then we get a much more random organization of our particles. Excuse my dodgy diagrams. But these ions can then move past each other. Okay, so if you melt an ionic compound or you dissolve it in water, the ions can then move and therefore they can conduct electricity. So metallic bonding. So we've got here, remember, before we labelled these as delocalized electrons. And that means they can move up and down between these layers of the ions. Because it can move, so it's the delocalized electrons that can conduct electricity. Okay, so now we can fill in a similar table about conducting electricity. So pause the video and complete this table. Okay, so just check that you've filled in the correct answers, and I'll just do another example on here. So we had water before, let's have carbon dioxide now, giant covalent. We could have graphite as an example. Ionic lattice, we could have MgBr2, and metallic, let's have sodium this time. Okay, so there's a separate video where I explain how to answer this 6-mark question. So can you please go away and watch that? And that will enable you to then answer this question. So once you've answered this question, if you email it to me, either if you've written it on a piece of paper, you can take a photo of it, or if you've done it on a Word document, you can email it to me. Right, so one last question for you to have a go at. So this question is about different substances and their structures. So all you've got to do is pause the video and draw one line from each statement to the diagram show which shows the structure. So pause the video now before I go through the answers. Okay, so if it's a gas, you need the particles very far apart and not touching, so that's going to be that one. Liquid, they need to be random but close together, so that's that one. You've got an ionic substance, you've got a repeating pattern of positive and negative charges, so that's that one. And the solid metal, we need rows of positive metal cations with delocalized electrons. Now, I don't think this is a particularly good diagram. So the substance is a solid metal, so it's going to go to that one because that's the best fit. But really, it should have delocalized electrons for that to be a good diagram. And then this one here that doesn't go to anything, you should recognize as the structure diamond. Okay, thank you for listening. See you next time.